Hello guys, I hope you're all doing well and I hope everything is okay with you. So this video will be, in this video I'll be solving 10 problems on transverse waves, which is covered in chapter 16. These 10 problems were specifically chosen by Professor Kunwar to be our class quiz. And according to him, it covers all the important points in the chapter. I want to make a little announcement. I will be changing the channel name from KFUPM Academy to Khayat Academy. And that's because I don't want to get into trouble with the university, into legal trouble, because I'm using the university name. And this is not an official channel, it's a personal channel, it's my channel. And that's it. Let's get these problems. And you'll find these problems in the description below. There are 10 problems, and I'll be solving them in order. Let's get going. Okay, so in this problem, it says that we have a wave going through a string. And it also says that the time for the particle to go from the maximum displacement, this is the y-axis, this is the x-axis. So we're talking about the displacement in the y-axis. So the maximum displacement in the y-axis is either this or this. You can choose whatever you want. Let's call this A and let's call this B. So in this solution, I'll be choosing A. So in the problem, it says the time for the particle to move from the maximum displacement to zero displacement is this time, 0.541 seconds. And this is the only given in the problem. So when you solve problems, the first thing you do is you list your givens. What is given in the problems? Because physics is just a collection of equations, and no matter what problems you have, there will be givens, and you will be using these givens and plugging them into the equations that you've studied to get your answer. So we have one given, pretty simple. So now the tricky part is to realize that moving from maximum displacement to zero displacement is equivalent to 1/4 of the whole wave. So this is 1/4, this is 1/4, this is the third fourth, and the fourth makes a complete cycle. The wave was going up from here, and it's repeating itself here. The particle that wave was going up. So realizing this pretty much solves the problem, because if you're doing fourth of the wave during the displacement from maximum to zero, then that means you're doing the period over 4. And this is also equivalent to 2 pi. And it's also equivalent to lambda over 4. This here is equivalent, this length is equivalent to lambda over 4. So if it takes 0.541 seconds to finish a fourth of the wave, or fourth of the wave, then you just multiply this quantity here by 4 to get your answer, not the answer, to get the period. So just multiply this number by 4, 0.541 times 4, and that's going to be 2.164 seconds, and that is equivalent to the period. The period is the time for a particle to make a complete wave or a complete cycle. Now, once we have found the period, all we need to do is to take the reciprocal of the period, which is 1 over t, which is equivalent to the frequency, and you just plug this number to your calculator, and you'll be getting 0.462 seconds, and that's your answer. Okay, so problem number 2 is a little bit more complicated, but it's still easy. We haven't got into the hard problems yet. So the problem is asking to find the frequency of a wave in order to generate this amount of power. So we're solving for f, the frequency, not the angular frequency. And we know that frequency and angular frequency are related by this equation. Solving for a frequency that generates this amount of power. So first things first. First, you list your givens. So unlike the first problem, in this problem we have so many givens. It says in the problem that the mass of the string is this, and we're given a tension of 36 newtons, and we're given the amplitude in millimeters. So we want this in SI units, so we multiply this by 10 to the negative 3, and we get this length in meters. And we're given the length of the string to be 2.7 meters, and we're given this amount of power. And we're asked to solve for the frequency that generates or gives us a wave that has or generates this amount of power. So once we've listed the givens in the problem, now let's list our equations, or the equations we're going to use. So we know that angular frequency is related to the frequency by this equation, so we list it. And we know mu is m over L, the mass over the length of the rope. And we're given the mass and the length of the rope, so we can easily calculate mu. And if you plug this into your calculator, you'll be getting 0.09. So what's the unit? Kilogram per meter. And once we have calculated mu, now we can calculate the velocity of the wave, which will be using the average power equation. So all we need to do is plug in the tension, which is 36 newtons, and we take this number and put it here, and plug the whole thing into your calculator, and you'll be getting 19.33 meter per second. Okay, now we're ready to solve the problem. So we're solving for f, okay? So we need to isolate f into one side of the equation and everything else in the other side. So first, let's write this in terms of f. So omega is basically 2 pi f. Square both sides, square whatever is inside the brackets, and you will be getting 4 pi squared. And yeah, there is an f biscuit. So the f is squared as well. So let's isolate f. So let's put f here. And this will be equal to the square root of the average power over everything here except for f. Okay, so there is a 1/2 here, so we have to multiply the average power by 1/2. And then we divide the 2p by, well, everything here except for f. So that will be the amplitude squared times mu times the velocity times 4 pi squared. Okay, so you just now plug things in and the problem is pretty much solved. Okay, so if you plug your numbers into your calculator, you'll be getting 194.16 hertz, which is the unit for frequency. So this is the frequency that we need to generate this amount of power. For problem number 3, it's an easy problem if you know how to solve it. Like if you understand the equations we get when we have interference, when we have wave interference, and in this case we have wave interference. Two waves are moving in the same direction. For example, we have two waves moving in the positive x direction. So if we have two waves moving in the same direction and they interfere, then you take a formula straight out of your formula sheet. This is the amplitude formula, and it should be multiplied by sine blah blah blah, I don't remember. But this here is the amplitude formula. You take it straight out of your formula sheet. So, and all you need to do now is to plug numbers in. Like, we're given that the two waves are out of phase by pi over 6. Pi over 6 is equivalent to 30 degrees. If you're more comfortable with degrees, then work with degrees. But make sure you change the setting in your calculator to degrees or radian. And now it's time to plug things in. Like, we have this is the amplitude of the two waves, the common amplitude. They have to have the same amplitude. And we're given the amplitude in centimeters. And the question is asking you to express your answer in centimeters, so we don't need to multiply this by 10 to the negative 2, because that's going to be in meters. Okay, we don't need to convert units here into SI units. So let's just plug this as is. 0.4 time cosine 30 over 2. And if you plug this into your calculator, you'll be getting 33.6 meters. And that will be the amplitude of the resultant wave after the interference. This value. And that's it. Alright, so problem number 4 is a relatively hard problem. And it involves a couple of tricks that you need to know already before solving it. So first thing first, as we always say, and first thing is to list your givens. So if you read the statement of the problem, you'll see that it's given that the particle at the point we're interested in is moving to the downward, and which means it has a negative velocity. So moving downward means we have a negative velocity, and this is very important to understand because we're given the equation of the particle. So if we're given the equation of the particle, then we are also implicitly given the velocity equation, which is just the derivative of the equation of the particle. We're also given that time is 0 and x is 0, and we're given that the displacement in the y-axis is 0 as well. So let's now differentiate this equation to get the velocity equation. So the derivative of this with respect to time will be negative omega times ym cosine here kx minus omega t minus phi. Okay, so now we have the equation of the velocity, and we know that t is 0 and x is 0, which reduces the equation into this minus omega ym cosine minus phi. Because these terms cancels out, and this is our velocity now. So we know that the velocity must be negative, and which means that cosine here must be positive. And we know that cosine, this is the unit circle, okay? So cosine is positive in this quadrant and in this quadrant, the first one and the fourth one. So our angles should be from 0 to 90, and they should be from 270 and 36 and, or 360. So now we're given a couple of angles here in the choices, and so we can't cancel this out because it's not in our range of angles. Okay, so 90 is not in the range as well because cosine of 90 is 0, and which gives 0 velocity. And we want the velocity to be negative, so this is out. Now 45 is in the range, it's between 0 and 90. But the problem with 45 is that if you plug 45 into the displacement equation, you're not going to get 0. And we want the displacement to be 0. So 45 is out as well. Now, I already know that this is the right answer, but I need to explain why this is wrong first, before I go to the right answer. So, if you have a number like this, if you subtract 360 from it, you're gonna get 90. So it's like you start from here and you go through 360 degrees, and then you go 90 degrees. So this number over here is the same as 90, so it's out. Now for this number, 720. 720 is basically 360 plus 360. That's going to give you 720, which means we go from here, make a full cycle, and then we go again and stop here. So this is equal to 0 degrees. And if you plug 0 here, you're going to get 1, and the velocity is going to be negative as required by the question. And if you plug 0 here, the displacement is going to be 0 as well, because sine of 0 is 0. So that's our answer, and that's it. That's the question. Okay, so problem number 5. So this should be 5 here. It's a pretty involved problem, and in my opinion, it's the hardest problem of these 10 problems. So we're given a lot of information in the problem statement. First thing we're given the wave vector. So the wave vector is k, okay? If you don't know this, you should know this by now, that the wave vector is k. So if we have the wave equation, yx of t is equal to ym sine kx minus omega t. And when we say wave vector, we mean this value, okay? Is equal to 4. And we're also given that the transverse speed is equal to 28 when the displacement is this value, and when x is 0. And we're also given that the transverse speed is 0 when the displacement is 0.04. And x as well, x should be 0 as well. So here, this is very important here to understand that when the velocity is 0, if you have a transverse wave and the velocity is 0, it must be, the particle must be at a peak, either in the top or in the bottom. So the velocity is only 0 in the peak, okay? If you have a wave, the velocity is 0 here, 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 and here. At any other point in the wave, the velocity cannot be 0. So if he says that the velocity, when the velocity is 0, the displacement is 0.04 meters, then this means that he's giving us the amplitude of the wave. Because the distance between the middle line here and the point where the velocity is 0 is the maximum distance, and therefore the maximum amplitude. So we're given this value, okay? We're given this value here. It's for 0.04. All right, so we're asking for the wave speed. So pay attention that these are transverse speed and this is wave speed. Wave speed is defined as k, or actually omega, is defined as omega over k. So we're given k here in the problem, so our job is to figure what omega is. And how can we do that? So we can have something like a system of equations. So he's saying at x is equal to 0, so which this term disappears. Our displacement is going to be this. So I'm going to make this here 0.02. So this is our first equation. So under these conditions, when the displacement is this value and when x is 0, the velocity or the transverse velocity is equal to 28. And we know the equation of the transverse velocity is just the derivative of the displacement equation, cosine negative omega t. And this here is our second equation. Okay, now let's solve this value. I mean, we can't solve for omega only, but we can solve for the argument of sine. Because we're given this number and we're given this number, and we can plug sine inverse into our calculator, and we can get this number, the whole negative omega times t. So if you divide both sides by 0.04, you're going to have 0.04 is equal to sine negative omega t. And if you take the inverse sine of both sides, sine inverse 0.02 over 0.04 is equal to negative omega t. Okay, just plug this into your calculator and you'll be getting 30. So the value of the argument is 30. So once we know the value of the argument, we can plug it here and solve for omega. And once we get the value of omega, we just divide it by k and you get your answer. So how can we solve for this? Alright, so the first step is to divide both sides by 0.04 times cosine omega t. And that's going to be 28 over 0.04 times cosine negative omega t. And if you plug this into your calculator, and we already know that negative omega t is 30, so this will be 30 here. Make sure your calculator is on the degree mode, not mode, I mean not the radian mode. Okay, so if you plug this into your calculator, you'll be getting something like 808.929, and that will be the value of omega. Now just divide this by 4 and you'll be getting the wave speed, which is 202. Almost. There is marginal error here because I'm supposed to have commas here, but I didn't write it. I don't know why. But this is your answer. Problem number 6 is a fun problem actually. But you need to know your physics. And if you know your physics, this is going to be a fun, short problem. So we have a stone that was dropped in water, which produced, imagine this is the surface of the water, and this is a wave, result from the dropping of a stone. So the problem is asking, after what time should we drop another second stone in order to produce destructive interference with this first wave? So when we say destructive interference, it means that we need a wave that is completely out of phase with our first wave. So the second wave should be something like this. In such a way, it should be placed in such a way that this peak is opposed with an opposite peak. So the resultant will be a line. So this is what we mean when we say destructive interference. So keep in mind that destructive interference only happens when we have a phase difference of pi. Okay, so when the angle or the phase difference between the two waves is pi, then we have destructive interference. Or alternatively, we could think of the equations. So if you want to get rigorous here, you could think of the equation we get when we have two interfering waves going in the same direction. And this is the amplitude, okay? So we want this to be equal to 0. And what should be here? What should be the angle? So the angle should be pi, okay? So because cosine of pi over 2 is equal to 0, which will make the amplitude 0, and we have destructive interference. Alright, so if you have an angle of 0, an angle of pi, then what does that mean? Like in terms of cycles and period and lambda, or the wavelength? Well, it means that we moved half a cycle. So we know a full wave is 2 pi, okay? It's like a full circle, and you take this half to the left, or to the right. So this is a full wave. So if you have pi here, that means half of the wave. And if you have half of the wave, then it takes 1/2 of the period. It's equivalent, like we could say that pi is equivalent to t over 2. So we should not drop the stone after the period divided by 2 seconds. And if you do that, we're gonna produce a wave like this that's shifted pi radians, and it will destructively interfere with the first wave. So we're given the frequency in the problem, and all we need to do is take the reciprocal of this. The reciprocal is basically 1 over this, which will give you the period, and if you plug this into your calculator, you'll be getting this number. So this number is the period, okay? And we're interested in the period over 2. So the period over 2 will be half of this number, which is going to be 3.4 something. 3.42 times 10 to the negative 3. And that's your answer. That is the time required to wait, after which you can drop the second stone, which will destructively interfere with the first one. Okay, so problem number 7 is a pretty straightforward problem. If you know your equations, you'll be easily solving this. So we're given in the problem that the linear mass density is equal to this number, and this number is given as in gram per meter unit, and the SI unit is kilogram per meters. So we have to multiply this number by 10 to the negative 3, because we know that kilo means 1000. Try to get your prefixes straight, so this will significantly help you in changing units. Okay, so the linear mass density is 13 times 10 to the negative 3, and we're given this equation. And if you know your equations, you will know that this value here is k, and here is omega. So we're asked to find the tension in the string. So we know that the velocity of the wave is equal to omega over k, both of which are given here. So if you divide omega, which is 7.8 over k, which is 8.3, you'll be getting the velocity of the wave, which will be 0.94 meters per second. Okay, so now we have the velocity, and this equation is the equation that will be used to find the tension. So if you square both sides here, you'll be getting v squared is equal to the tension over mu. And just multiply both sides by mu. in order to isolate tension, or T. And we already found this value to be this value, and this is given in the problem. So plug this into your calculator, you'll be getting 1.15 times 10 to the power -4 newtons. And that's it, that's your answer. Okay, so problem number 8 is a standing wave problem. And if you have memorized your standing wave equations, especially this one, the one for frequency, then you'll be able to easily solve the problem. So we're asked to find the length of the string, which is L, and we're given two things. We're given the equation of the standing wave, and we're given the number of the harmonic, or the harmonic number, which is n, is equal to 17. Okay, so if we need the L value, so we just solve this equation for L. Okay, so divide both sides by NV, which will be equal to 1 over 2L. Then you can cross multiply, so NV is equal to Fn times 2 times L. Then divide both sides by 2Fn, and you'll be getting L. So we have N, which is 17. We have the velocity, which is omega over k. If you know your standing wave equation, then you will be knowing that this is k and this is omega. So if you divide these two values, which is 15 over k, which is 2 pi, you'll be getting the wave speed. Okay, so I haven't calculated it, but you'll be given a number, okay? Let's calculate it. I have a calculator. Sorry about that. 15 over 2 pi. Yeah, it will be something like 2.38. And you could just plug this in, and we need to find this frequency. So we already know that from our equations. I don't know if this is in the equation sheet or formula sheet, but you have to know that the angular frequency is equivalent to 2 pi times frequency. So if you want to find the frequency, you're going to have omega over 2 pi. Omega is given in the problem or in the equation to be 15 over 2 pi. Which will be sampling, which will be 2.38. Okay, so if both the frequency and the velocity is equal to 2.38, then they can cancel out, and we have n over 2 to be equal to L, or 17 over 2 to be equal to L, and that's going to be equal to 8.5 meters, and that's your answer. Number 9, which is our second to last question. So keep up the good work, guys. Keep the video on. So it's a standing wave question, okay, and it's a pretty fun question. Okay, so we're given the frequency of a standing wave, and we're given the distance between the 6th node to the 17th node, which is equal to 148 centimeters, and you have to multiply that by 10 to the power -2 to get into meters, which is equal to 148 meters. Okay, so what does it mean to have a distance, like the distance between the 6th and the 17th node? Okay, so we know that the distance between one node to another node, imagine that this is your standing wave. So what does this distance represent? If we say that the whole distance from A to B to be equal to lambda, so the distance from here to here is lambda, then the distance from here to here is lambda over 2, okay? So we know that from this graph and from this understanding of standing wave that the distance between two nodes is equal to lambda over 2. And this applies to any nodes, any two nodes on the wave, this and this, etc. So now we already know that the distance between two nodes is equivalent to lambda over 2. And if you notice that this distance covers half a circle. Half of a circle is equal to one harmonic number. If n is 1, then we have a standing wave like this. Forget about that, all this, and let's focus on this. So if the harmonic number is n is equal to 1, then we have a wave like this, and our length of the string is going to be lambda over 2. So if you multiply lambda over 2 by your harmonic number, you'll be getting the distance of the string. So for example, here we have 1, 2, 3, 4, 5, 6. Our harmonic number here is 6, n is equal to 6, because we have 6 half circles. So if you want to get the length from here to here, from point A to point B, then you multiply lambda over 2 by 6, which is our harmonic number. So we're given in the question that the distance between the 6th node to the 17th node is equivalent to 184. So first we could get the string length when our harmonic number is 17. So we could multiply 17 times lambda over 2. And then we could subtract from it our string length when the harmonic number is 6. So that's going to be 6 times lambda over 2. And if you do a little bit of algebra, you'll be getting 11 lambda over 2. And that's equal to 1.48 meters. If you multiply both sides by 2 and then divide both sides by 11, you'll be getting your wavelength. And that's going to be 0.269. And now we just need to plug the wavelength into this equation. We already know that the velocity of the wave is equal to f times lambda, and we're given the frequency to be 262. Multiply that by the wavelength, 0.269, and that's going to give you your wave speed, which will be 17.5 meters per second. And that's one important thing that I need to point out about this equation right here. If you're gonna use this equation to calculate the length of the string you have, then you have to start from the second node. You can't start from the first one, because if you say that this is the first node, then you're gonna plug 1 here, and 1 times lambda over 2 is going to give you lambda over 2, and this number right here is meaningless because we started from here. Like there's no string like before A. So you have to start calculating from the second node. So think of this node as being the first one, and this one is the 0 one. So if you plug in the number of nodes, you're gonna get the length of the string. So if you plug here 1, you're gonna get lambda over 2, which is true. This length right here is lambda over 2. And you could understand this equation your own way, I guess. Just look at the standing wave and think about the standing wave and the equation, and you will get to some sort of understanding, hopefully. Alright, so our last problem here is problem number 10. And it's a pretty straightforward problem as well. So it says that we have a wire and it's connected to a pulse generator. So this device right here can generate pulses. So we can have a wave, transverse wave here. And at the other end, the wire is connected to a mass of 8.1. And if you multiply that mass by the gravitational acceleration, which is 9.8, you'll be getting some value right here. So let's multiply that out times 9.8. That's going to be equal to 79.38 newtons. Okay, so now we know the tension of the wire, and we're given that the length is equal to this value, and we're given the mass of the wire. Okay, so we're asked for the time it takes the one pulse to reach the end of the string. So how can we do that? Alright, so we know that the velocity is equal to the length over the time. Okay, so if we solve for the time here, that we're going to get that t is equal to L over the velocity. So we already know the length of the string. We just need to figure the velocity out. Well, we have the tension, we just calculated it. We need the mu, or linear mass density. So linear mass density is just the length of the string over the mass of the string, which are given here. So all you need to do is plug these numbers into your calculator and you'll be getting this number, meters per second. Alright, so once we have found the velocity, now we can plug the velocity here and plug the length here, and we'll be getting that time, which is 0.206 seconds. So the length is basically the length of the wire. Here the distance required to be traveled, like from here until the end of the wire, which is required by the question, is L, okay, which is given in the problem. And that's it. That's our last problem. And I hope you enjoyed and get benefit from this video. And our conceptual explanation will be coming soon for chapter 17. So good luck to you all, and I hope you do great things.